we're going to see the electric dipole moment. The electric dipole moment is usually in a molecule that is polarized. That is, we have, for example, the carbon monoxide. The oxygen is slightly negative in this configuration of the molecule, and the carbon is slightly positive. So even though this molecule is electrically neutral, there is a polarization of the molecule in this direction, in the direction of the electric field. The electric dipole moment, written with a letter P, the magnitude of this is the charge times the distance between them. We will say that the electric dipole moment is a vector that has this magnitude, and the direction is in the direction of the electric field. So we have, for example, here the molecule of water. You have the oxygen, hydrogen, hydrogen. Here we have slightly negative charges, and here positive charges. So the electric field is something like this. This is the direction of the electric field. So the dipole moment would be 1 times the distance of, because the charge is 1 coulomb, times the distance here in the direction of the electric field. So these molecules are called polarized molecules. We can define the torque because these molecules are neutral. So the force, that is Q plus times the electric field, and Q minus times the electric field. If the electric field is uniform, the force is the same, so there will be no net force, but there will be a net torque, because the torque, the torque tends to make that the molecule be aligned with the electric dipole. So the torque is the force, that is Q times the electric field, times the distance. Now the distance, this is the distance, so it's d over 2, plus the other one, that is the force, that is the other Q times the electric field, times d over 2. So the torque is Q times E times the distance. The Q is like force. The torque tends to align them, so the maximum torque is when it is perpendicular to when the electric dipole moment is perpendicular to the electric field. Look, here we have charge and here we have distance, so the torque is the electric dipole moment times the electric field. Cross product the electric field, because the maximum torque is when these are orthogonal. So the torque tends to align the electric dipole moment to the electric field. And so you can think now as the work done in trying to align them, that would be the integral from going to theta 1 to theta 2 of the torque dot dt. Now actually we need to put a negative sign here because the torque is going in the opposite direction, and the work done then would be, this is the integral from t1 to t2, theta 1 to theta 2 of the dipole moment times the electric field, and because here I have a cross product, I will put a sign theta. So this is the same as the theta. So this is the same as the these are two constants, the electric dipole moment and the electric field, times the integral of this is negative cosine, so this will be plus. So times the cosine of theta evaluated from theta 1 to theta 2, or whatever you want, and then you just take the difference. So this will be the work done if we want, for example, to move or to rotate the polarized molecule in a direction opposite to the electric field, so that the dipole moment is not aligned with the electric field. The work done would be this. So the torque is the cross product of the electric dipole moment and the electric field, and the electric dipole moment is the charge times the distance. If the electric field is not uniform, there would be not only a net torque but also a net force.